this second universal law that tells us something about the universe as a whole. Okay, so George Gamow, who was a Russian who immigrated to the United States and was working on the issues of radioactivity and nuclei, and discovered that you could, if you had high enough energy reactions to overcome the electrostatic forces, you could actually have collisions inside of nuclei and change one nucleus and therefore one element into another. You could transmute the elements, which was the dream of the alchemist. But you could do that on a routine basis, provided you could get to a high enough energy and you could get up a high enough density to have collisions. And so he asked the question that I asked, where did all the elements come from? And he said, if there was a Big Bang, that would be the ideal place, because if you take the universe now and compress it by a very large amount, it'll be much denser, but if it was warm now, it'll be very hot when you compress it. And he said that will be just the things you need to have nuclear burning of primordial material to make things. And so he worked with his graduate student, Ralph Alpha, and they worked out the theory, and they determined that when they did the calculation, that 75% of the universe should be made out of hydrogen, and 25% should be made out of helium, and just a tiny smattering of other very light elements should exist, and that's all there should be. That's because there are no stable elements, stable nuclei in the mass range from 5 to 8, and you couldn't get through that bottleneck. And at the time, he was arguing with Sir Fred Hoyle, who wanted to make the universe not in the Big Bang, but with a steady state, and he wanted to make the elements in the stars. And he graded the two of them on the quiz, and he said that he and Alpha got a 99% on the quiz because they could explain 99% of all the elements in the universe, maybe the hydrogen and the helium, and that Hoyle only got 1% because he could only explain the 1% of the universe, which happens to be carbon, nitrogen, oxygen, iron, the things that are in this room. Right? So it turns out we need both the Big Bang and we need stars in order to make what we see. And when he went to publish, he called up his friend Hans Bethe and asked him to be a co-author so they could have the alpha, beta, gamma paper. Those that know Greek, you know that's a science joke. So here's a picture of Gamow, Alfred Herman, and Fred Hoyle, who's grumpy for only getting 1%. But, you know, he was often in arguments. But one important part of their prediction that Alpha and Herman went through, calculated several times, was the temperature of the universe today should be around 5 degrees above absolute zero. This room is about 300 degrees above absolute zero. The sun is about 6,000 degrees above absolute zero. So 5 degrees above absolute zero is extremely cold. Right? But they predict that's the radiation that should be left over from the beginning of the universe. Okay, so there was no way to measure that, but 20 years later, in 1964, Bell Telephone Labs launched an experiment, which was called a Telstar satellite, and it was a test to see if it was possible to send radio signals to a satellite and have them relayed back to the ground. That was the idea. Was if you could do that, you could have communication satellites. We know that that was a successful experiment because we use communication satellites all the time. And as soon as it worked, they thought, we need to know how bright is the night sky behind it, because we have a certain weak signal coming from the satellite, and we have a certain noise coming from the sky, and if the signal-noise ratio has to be above 5 in order to have the error rate in the communications be sufficiently good, if the noise behind in the sky is very high, this will not be economical because satellites couldn't produce very much. We need radio astronomers to measure the brightness of the night sky so we know whether we can proceed with this. So they hired 2 brand new PhDs, Arno Penzias, who's shown on the right in this picture, and Bob Wilson. Arno had been out for a year. Bob Wilson actually just graduated when they hired him, and they said, please come to Bell Labs and measure the temperature of the sky. And so they got there, and their boss started bugging him immediately saying, what's the temperature of the sky? And the antenna already existed for Telstar, and a very good receiver already existed for Telstar. So they said, we'll make a measurement of the brightness of the night sky at 7-centimeter wavelength and get them off our back, and then we'll go make measurements at 21-centimeter wavelength, because we know there's hydrogen in the galaxy, and a map of the hydrogen in the galaxy would be a great thing to do. So they quickly made a measurement at 7 centimeters, and to their surprise, no matter where they looked, they saw a signal of 3 Kelvin, and they could show it was not coming from their equipment, because they had very good equipment and they had a good reference load, and they could compare a 4 Kelvin reference load with liquid helium which was rare in those days, to the 3 Kelvin from the sky and know that there wasn't a mistake. And they even went and replaced part of the antenna to make sure it wasn't that. They did many tests and were able to show it wasn't coming from the equipment, it wasn't coming from the galaxy, it was coming from the sky. And then they ended up publishing the discovery, which they had got the Nobel Prize for 13 years later, which was the relic radiation, which was interpreted to be the relic radiation from the Big Bang. At least people hope that. And it took 14, 15 years before it was awarded, because people had to begin to establish that was what it was. And it was a milestone. I was a young student. I thought, that's great. It means the Big Bang is right and the steady state's not right and these other models are not right. And I went back to my studies. But 2 years later, I went down the street from MIT to Harvard to hear a talk by a graduate student who was just graduating named Joe Silk. And there he extended and sharpened the question for me and told me this was actually an interesting problem. And the problem, he entitled his talk, Fluctuations in a Primordial Fireball. And the reason he did that was to point out what we now know. We didn't have good pictures like the one I showed you at those times, but there were galaxies, and galaxies had the form, and you had to have some model. If you're going to explain where the elements came from, you also have to explain where the galaxies come from. And so the problem with general relativity is it didn't know how to make galaxies, and it particularly had a problem if this radiation, this microwave radiation, was a relic radiation from the Big Bang. And it's a very simple problem. If I take you and I put you in the sun, what happens to you? You get burned to a crisp. Even worse than that, electrons are stripped from your atoms, and then the radiation pressure blows you, spreads you out like a big cloud. So you're better put together than a galaxy. You're more strongly bound together than a galaxy. So if I were to put a galaxy in something big enough to hold, a sun that was big enough to hold a galaxy, like the primordial fireball, the galaxy would be vaporized, and its atoms spread uniformly across space. And so if I go back, instead of just a factor of 1,000 from the present time to 3,000 degrees, that's enough to do that. If I go back another factor of 1,000 times brighter than the sun, like a nuclear weapon, that's enough to completely ionize everything and spread the atoms absolutely uniformly everywhere. And if I go back another factor of 1,000, that breaks up the nuclei. That's the nucleosynthesis. So not only do you not have galaxies, but if this fireball, you have to go through in the right direction, build up first the nuclei, then you build up the atoms, and then you can build up the galaxies, and you have to have that. And so then the question is, how do you do that? And his answer is, you must have these fluctuations, and they must somehow have to survive through this fireball in some primitive form, and then you can start having galaxies form once the radiation releases the matter in order to make galaxies form. But as long as you're trapped in something as bright as the sun, you can't make a galaxy. It just gets blown apart. And so, to me, right, this says this is an important problem. Either this radiation doesn't come from the Big Bang, or it can let you see the beginning of the universe. To my colleagues, they're saying, this is a field that's not ready yet. This will never amount to anything. They're just guessing, right? And so it's just a difference in perspective. And you have to have a little better judgment than that. You have to see it's actually possible to build equipment in a shorter time tail in 20 years, because most people's careers don't last that long. Okay, so here's our primary tool. Our primary tool is that the universe is very big. So in this picture, the Earth is in the center. And if I look out to the sun, and I take a picture of light coming from the sun, I get an image of the sun as it was 8 minutes ago, because it takes light 8 minutes to get from the sun to the Earth, right? If I take the nearest 50 stars, on average, it takes 10 years, right? Now, if you take a photograph and you don't get the picture, it's only photographs that come in are 10 years ago, you're not as happy about that as having ones that come within a minute, right? Well, now with digital cameras, you want it to come within a second or two, right? But that's not so bad. If I go out and I look at the Andromeda galaxy, which is down here, it takes light 2 million years to get to us, right? If you took a picture of the Earth 2 million years ago, there would be no lights, no electricity, there would be no people, no Great Wall, no temples, nothing, right? There was no humans on the Earth 2 million years ago. And so if you had an image of our galaxy or from 2 million years ago, you wouldn't see any evidence of humans at all, right? And of course, if you take a picture of our galaxy now, the Earth is so insignificant you don't see evidence of us, but if you could zoom in, you would. So just the size of space itself allows this. But now, if I go out to a typical galaxy, it could take, right, a billion years or many billion years. If you look as far as you can see, you can look 14 billion light years. You're looking back 14 billion years. You're looking back to when the universe was much smaller, therefore hotter. So eventually you can only look back until it's ionized, like the surface of the sun. You can see the surface of the sun, but you can't see inside of it. It's like looking to a cloud. The light scatters at the edge of the cloud, and you can't see into the cloud. And that's what the universe is. So in this picture, our plan would be look at different distances, look at spheres around us at different distances, get a sample of what the universe looks like, and plot that as at the distance divided by the speed of light, and that's the time that it is back in history. And you can start at the very early universe, right, when the universe is an embryo, and you can take pictures along the way, and you can see the development of the entire history of the universe. You can plot out like the life cycle of the universe. So that's our plan. And where are we? Well, I started working on the problem of making an image of this part of the universe, and we now have a very good image, and I hope at the end of the month we put up our 3rd generation satellite and we'll make an extraordinarily good image of the beginning of the universe with extraordinary precision and many wavelengths so we understand it. And we've been making surveys of the nearby region, the galaxies that are relatively nearby, and if I rush, I will be able to show you pictures of the nearest, a sample of the nearest 1 million galaxies, and you can see where they are and what they look like. And so in between, we're starting to build up surveys to look at greater distances and different techniques for looking at different distances. So just to reiterate, here's the idea. We live here in the present in a spiral arm and a spiral galaxy about this location, sort of in the center of this sphere. If we look out further, we see around us in a volume relatively close by relatively mature galaxies. There's still some galaxies being born, but most of the galaxies have been around for quite some time, and they developed and matured quite a lot. If I look further out, I see the beginning galaxies that are just forming. They have irregular shapes. Some are small. Many of them will merge together to make the more developed galaxies later on. And so this is, of course, schematic because there are 100. That picture I showed you had only 2,000 galaxies in it. If I did tile the whole sky with pictures like that, I would see over 100 million galaxies. I would see more galaxies than there are stars in our own galaxy. Remember, there were only 4 stars in that picture, and there were 2,000 galaxies. And so modern galaxy, more developed galaxies around it, just beginning galaxies, and then you look out and you see the very embryo universe, and if you could look any further, you would see the very beginning of time, right? The very birth of the universe. And you can't quite see that. It's shrouded just like you can't see the center of the sun. We can't quite see there yet, although there are other ways to try and probe that. The same way that you can take an acoustic picture, right? You can do an ultrasound of an embryo in the mother's womb. You can do an ultrasound of the universe and look at the sound waves, and that's what these speckles represent, sound waves that come to us from the beginning of the universe. So we actually are able to probe to a small fraction of a second, but it requires some interpretation of what we do. Okay. So this is the beginning of developing more sophisticated tools in order to make the measurement. It turns out we're trying to look at a signal which is the cosmic microwave background, which is 3 degrees above absolute zero, and this room is 300 degrees, so we're already down by a factor of 100, and we're going to try and measure that fairly precisely. And now we're going to look for tiny fluctuations in that. At the time, we thought it would part in 1,000, so we'd have to get down to 10 to the minus 5 of the background. It turns out it was much lower than that, so we had to do better than a part in a million. So to measure the temperature of the sky over here to a part in a million and temperature of the sky over here to a part in a million and compare is difficult, so we do differences. We do a differential.